In the fourth part of this video on recursion, we will discuss when recursion is best used, which is when it both simplifies the solution but does not introduce any inefficiency. We will examine two such examples. Although recursion has the potential to simplify problems, it also can introduce inefficiency. In part 2 of this series, we saw that recursion is very undesirable when it involves duplication of work, because that is when significant inefficiency can be introduced. If a problem can be solved with constant memory, the iterative version will always be more efficient in terms of memory usage. Consequently, recursion works best on problems that cannot be solved with constant memory. In this video, we will examine two such problems. The first is the reversal of a list of values. The second involves the evaluation of prefix expressions. Because expressions can contain nested sub-expressions, nested to any depth, the amount of memory required is also unbounded. Another way to characterize problems that benefit most from using recursion is to say that they are those problems that would require the explicit use of a stack when solved iteratively. Now, let's consider the reversal problem and see how it meets the requirements that we have just outlined. Specifically, the example that we will use will reverse a list of integers read in from a file. First, a program that performs reversal cannot be solved in constant memory. Because that file can be of any length, and because all elements of that file must be saved in memory, the amount of required memory is unbounded. If we wrote an iterative program, it would require the explicit use of a stack. It would require two loops. The first loop would read in values from the file and push them onto the stack. The second loop would pop the values from the stack and display them. Using recursion, the program implicitly makes use of the compiler's runtime stack by stacking the values that are saved in a local variable of the recursive method, which means that there are multiple copies of the local variable on the compiler's runtime stack. Let's now examine this program that reads in a file of integers and displays them in reverse order. Unlike what we have done in previous examples, we will not include an iterative version of this program, although we did describe how it would be implemented. We begin with the main method. It simply opens the file and calls the recursive method reverse. Next, let's examine the recursive method reverse. Notice that it is supplied with a scanner object that defines the input file. The first check implements the base case. When the file is empty, the recursion stops. Next, an integer is declared and read in from the input file. Although most of our previous examples did not contain a local variable, this one does. What is important to realize is that there will be as many copies of the variable value as there are activations of this method. This line appears directly before the recursive call, which means that this line will be executed repeatedly until the base case is reached, before the line after the recursive call is ever executed. This is the recursive call. It separates the code that is executed on the way into the recursion from the code that will be executed on the way out. Finally, this statement displays the value contained in the variable value. Because it appears after the recursive call, this statement will be repeatedly executed as the recursion backs out. Moreover, it will be executed in the reverse order. The reason is that function returns occur in the reverse order in which the function calls were made. Now, let's run this program. Now, let's open the input file to verify that the output is indeed the reversal of what was in the input file. We see that it is. Before we look at our next example, let's begin with a brief discussion of prefix and postfix expressions. Some programming languages like Lisp use prefix expressions instead of infix. Because Lisp requires parentheses, expressions containing arithmetic operators can have more than two operands. Many early scientific calculators used postfix or reverse Polish notation to input nested arithmetic formulas. One advantage of prefix and postfix expressions is that they do not need parentheses, nor do they need rules about operator precedence or associativity. They can only be parsed in one way. With infix expressions, the operator is placed in between the two operands. But in prefix, the operator comes before the operands, and in postfix, it comes after. Now, let's examine the prefix expression and its associated recursion tree that we will use as input to the program example. Here is the prefix expression, plus minus 5, 2 times 3, 4. Shown below is its arithmetic expression tree. It is also the recursion tree that will result from the execution of our program example. Each node of the tree represents one activation of the recursive method. Inside the node is the token that will be read in on that activation. Let's see how this evaluation will be performed. All the leaf nodes contain operands, so they are base cases. So the leftmost one containing 5 just returns 5, and its sibling returns 2. The activation that reads in the minus subtracts them and returns 3. Similarly, the two rightmost leaf nodes just return their values, and the activation that reads in the times multiplies 3 times 4 and returns 12. Finally, the activation at the root of the tree receives the 3 and 12, adds them, and returns 15, which is the value of the whole expression. Now we are ready to examine the program that will perform the evaluation of prefix expressions just like the one that we just discussed. We begin with the main method of this program. The first step is to prompt the user for the prefix expression and read it in. Next, we create a string tokenizer from that string. The advantage of using a string tokenizer is that it allows us to specify a collection of delimiters and have those delimiters be returned as tokens. The second argument is a string that includes all the delimiters. Notice that we have included the 4 arithmetic operators and a space. The third argument, which is true, specifies that we want the delimiters returned as tokens. This approach makes it possible to omit spaces between adjacent operators and operators adjacent to operands. Finally, we call the recursive method prefix evaluate, passing it the tokenizer and display the result it returns. Let's scroll down to that method. Because spaces are returned as tokens, we must first skip any spaces between tokens. Next, we check whether the first character of the next token is a digit. If so, this token is an operand, which is the base case. In that case, we convert the string to an integer and return that value. Next are 2 recursive calls to this method. What is returned by the first is saved in left, and what is returned by the second is saved in right. These 2 calls initiate the evaluation in the left and right subtrees of the arithmetic expression tree that we illustrated earlier. The final step is to perform the operation. Notice that the evaluation happens after both recursive calls. So when the program execution is moving back up the arithmetic expression tree. This switch statement is used to perform whatever operation corresponds to the operator that was read in prior to the 2 recursive calls. Next, let's run this program. Let's enter the prefix expression that we used previously. Plus, minus, 5, 2, times 3, 4. Notice that the program outputs 15, which is what we previously indicated was the value of this prefix expression.